Hi, welcome back. Today we have to do some instrument modifications. I have a micrometer that needs to be modified. This is a wall thickness micrometer. It has like a barrel shaped anvil and a regular flat moving anvil, and this is to measure the thickness of tubing, for example, or shell casings, stuff like that. The round anvil and barrel-shaped anvil gives a single point of contact on the inside, and then you measure the thickness with the moving anvil. And this one needs a large chamfer ground onto this anvil, which is kind of a simple task. We just undo the anvil from the micrometer, put this in a spin fixture, and grind a chamfer on here. Kind of simple. And then we have a Webster hardness tester. This is a hardness tester for softish materials, which works like a plier. I have never seen these before, and that's already in parts because I took it apart. And on this one we need to modify the lower anvil. This needs to be a smaller diameter, which will be a little bit of a problem because this is permanently bonded into the body of the hardness tester. I think we will cut it off, hard drill into it, and then put a new pin in it. That's what the customer requested and recommended to do. So we're going with that plan. Otherwise we can still throw a flame onto it and try to get the entire anvil out of the body. I think it's just a snug press fit and some epoxy on the backside. I don't think it's locked in there any different way. So we have to modify the anvil and also the upper guide which guides the indenter. I will put it together later when I'm done and do an indent on some brass so you see how it works. And also I want to see how it works because I have never seen it before. It has like a gauge which I think works like a pressure gauge here, which gives you a Webster hardness, and the manufacturer provides a chart to convert it to HRC, hardness Brinell, and I think hardness Vickers. As I said, I have never seen one of these before. Looks kind of nifty design. As far as research told me, a lot of people who do reloading themselves use them on cartridge cases after the resize or necked the cartridge and check if the brass has work hardened or is hard enough or whatever. I'm not a reloading person, so don't know about that. I know about instruments and about grinding, so let's start with the micrometer. If you have watched any amount of grinding videos here on YouTube, you know what these are. This is a spin fixture or a punch grinder, because they're often used to grind punch in tool and die work. They are a sliding V-block, rack and pinion, where you can slide the V-block. And they have a high precision angular contact bearing in here, which allows you to clamp a piece of work in here. Use the sliding V-block to put it exactly on center or off center if you want to grind an eccentric feature. Clamp it and then you can spin it to do your cylindrical grinding. Very nifty, very useful item, super handy to have, not only on the surface grinder but also on a milling machine for some high precision machining on small parts. They also do indexing, so you can do. They have like, I think, a 15-degree indexing with fixed positions, but they also have a graduated dial on the back here and a vernier. And they also have a mechanical lock with a socket head cap screw in here, which locks it between the positions of the fixed stop. So you can do a lot with these. You can grind, for example, hex profiles. You can grind squares, round profiles, all sorts of stuff. The Herrick grind awl is a very prominent manufacturer or example for one of these units. Found this on eBay. somebody removed the manufacturer tag, so I have no real clue what it is. But it has served me very, very well, and it's a very useful piece of machinery. So nice thing about these is they have a huge through bore. I think they have about 25, they have 30 millimeters of through bore, which allows you to put stuff like this micrometer barrel and anvil in here. So we check the V-block for cleanliness. The V-block has a large cutout in here, and this is for items that have a head, like a punch, ejector pins, things like that. But in this case we can just, at least I hope we can, no, I got into a little pickle. The micrometer spindle with the barrel does not fit in here properly. The end of the barrel hits the T-nut down here. Means I can't get far enough out the end to grind the chamfer. It would need to stick out at least this far to do a decent job here. So I could either modify the T-nut, make a split sleeve over the spindle here to raise it up a little bit further away from the T-nut, or use a completely different work holding solution, and I have one. So let's get the V-block out here. As you can see, this is just a hardened V-block with a rack machined into it and ground, and a spring-loaded T-nut here. The spring-load is just there to keep any backlash out of the system and keep the V-block from tipping over when you loosen the clamp screw. I purchased a very inexpensive ER25 Collet chuck with a flange type, and I hard turned the face on the back side to fit over the OD of the punch grinder. And I hard drilled 2 holes into it that match the M6 holes in the face of the punch grinder. So this goes on here, and 2 M6 screws go in here, and we finger tighten them just very mildly. The recess in the flange is bored oversized, so I can slide it around on the face of the indexer to adjust the run out, like a set-through chuck, just without the set-through feature. And now we have a Collet spin fixture. Let's see, where is the spindle? Here. This is a 6.5 millimeter diameter. So we can take a 7 millimeter ER Collet, which I happen to have. An ER Collet has, of course, 1 millimeter of clamping range. And I think, oh yeah, there's the assembly, and this even fits through the bore of the Collet chuck. That's okay. That's neat. That should work. Let's get a punch and a Collet wrench. Okay, that's solved the work holding problem. Now we can put an indicator on here and dial it in properly. So let's see, dial test indicator, 0.01 millimeter reading. Putting it on the top of the part. So yeah, we get some run out here. And I'm just using a soft soft-faced hammer onto the flange and shift the flange around until I get a 0 reading here on the indicator. So I clamp the spin fixture to the table of my drill press just so it doesn't move around when I do my indicating here. And soft-faced hammer, and I'm finding the high spot and the low spot. Low spot is at 5, high spot is at 16. So we split that in half. And with one approach we already got within like 20 microns. Okay, this is just a clearance chamfer, so I'm not going entirely all crazy on it. Note that I don't use the mechanical lock of the spindle or the indexing pin when tightening the screws. I'm always using a Tommy bar to counteract the torque from tightening the screw or the collet nut. I don't want to put all the strain from tightening an ER collet. ER 25 collet takes about a lot of torque to tighten it properly. I think it's in the 80 Newton meters range. Okay, that's fine. Put it on a surface grinder and grind the chamfer. Of course, it's a carbide faced micrometer, so we have to use a diamond wheel. Here's the Looney Tunes setup that I came up with to grind a chamfer. I have the punch grinder on a magnetic V-block that's directly on the table of the surface grinder next to the magnet. I tried to put it on the magnet, but then I'm missing about this much of column height to clear the work with the grinding wheel. So that's not good. So put it next to it. And since the punch grinder in the magnetic V-block is not ultra secure, I put two 1-2-3 blocks up here on the magnet, butted up against the punch grinder. The sides on it are ground, so they are a reference surface. Pushed it up against them, and I put a large clamp around everything. So basically the punch grinder is clamped to the two 1-2-3 blocks, which are held to the magnetic chuck. And the 45-degree angle is given by the magnetic V-block down here. This gives me enough clearance to work around here. I can access the hand crank for spinning my work, and everything is fine. So I'm going to plunge down somewhere in the center of the grinding wheel so I don't mess up the corners of the wheel. It's easier to dress the entire face of the wheel just to get a little bit of a nick out the center of the wheel compared to do a complete reconstruction with sharp outside edges on the wheel. Once the corners of the wheel round over to a significant amount, that requires a lot of work in redressing and reshaping the wheel. Since I don't have a flywheel dresser or a braked dresser, I use a piece of molybdenum, as Robin Rancetti did an excellent video on dressing super abrasive wheels. You should go and watch it if you have any contact points with super abrasive, either diamond or CBN. CBN being for hardened steels, diamond being for carbide, glass, stone, things like that. But today we are grinding carbide and a little bit of steel, which is really not ideal for a diamond wheel. The soft steel tends to grab the diamond out of the wheel and embed it in itself and rips the diamond out of the bond of the wheel. That's also the reason why, instead of using molybdenum to dress a resin-bound diamond wheel, you can also use soft, mild steel and just grind it. Grind it, and over time the wheel will break down and get a nice flat face. Takes forever. You can do that on an automatic surface grinder with downfeed very well. On manual surface grinder, it tends to be a pain. The molybdenum does the same. It rips the diamond out of the bond, but it's more effective at doing that. I know how much I need to downfeed, and I'm going to put some blue marker on here so I know when my wheel touches the work, because I see a tiny stripe of bare metal once it touches. So the idea is, run the grinding wheel, spin the work at a constant rate, going like climb milling, so work and wheel spin in the same direction, and then drop the wheel, make contacts around the DRO, and so on and so on. And also we are using dust extraction because, as I said, this is carbide and you don't want to breathe carbide. In fact, you don't want to breathe any metal dust, but carbide, tungsten carbide, is especially bad for you. But in reality, all kinds of dusts are very bad for you. So we hook up the dust extractor, which will catch most of it, and I'm also wearing an FFP2 mask, which is, I think it's equal to a KN95 mask. Ooh. Ooh. That's the setup I came up with to modify the hardness tester's body. We removed the indexing head from the FP1, and I clamped the body of the hardness tester right against the apron, so it's vertically. One strap clamped down here with some packing material because the side of this machine body is not even. This one is tightened down. This gives support, and I had the upper clamp loose so I can move it side to side to align this pin vertically. And I do the vertical alignment since I know that the head of my mill is trammed properly. I'm just moving the quill up and down. One could argue that it would be better to move the C-axis up and down, and that's kind of true, but moving the quill is kind of easier. So this is within 10 microns. It starts down here at +1 and falls to 0. So the body has to move a little bit over. And we can still do that. I'm losing the clamp. This clamp that holds the body against the apron. And I just give it a little tap. Oops. And that was a little bit much of a little tap. Okay, that's pretty much 0, 0, top to bottom. It's probably not crazy critical. So let's crank down on this clamp so it doesn't move on me when I start to do the hard machining on this pin. Now we need to center on the pin because we need to shorten it and then drill a hole. Finding center of a pin. Spindle is sitting somewhere and we're on a huge circle. So we start over here, indicator oriented 90 degrees to the travel, and we get the dial oriented so it's nice to read, and we just crank to 0, like here. At this point we zero out the DRO, and we drop the part or raise the quill and go 180 degrees. Now we crank over and we crank to 0 again, right here on 0. Now we have some random x value, which is a function of the circle which the indicator spins on and the diameter of the feature we're indicating. So, but we want to find the center point of this. That's easy. We take the x-axis and we use the half function. Now it's just half the value. Now we drop the axis and crank to 0 in the x direction. Now we rough a line in the x direction. Now we do exactly the same thing in the y direction. Means going this orientation, cranking out, raising the axis, cranking into 0 and 0 the DRO. Dropping, spinning 180. Hopefully our travel is... Thank you, Mr. Deckel. Y-axis travel is too short because the part is very close to the column, of course, because we're clamping against the apron. So I changed the radius where the indicator spins on, and we're going to do it again in the Y direction. X direction doesn't need to be changed. So we go in, crank to 0, Y-axis 0. Spin 180 degrees, roughly. Go into 0, and split the dimension in the Y direction. And we crank to 0. And now we are half decent on center to do our proper indicating. So now we can drop the spindle, and when we spin the machine now, we're pretty much there. Let's bring the indicator into contact. 0 out the dial. And let's see, 0, 40 microns, plus 20, minus 20. So we're in both directions about 40 microns off center, kinda. And now it's just a matter of playing with X and Y until we don't get any change in the reading when we sweep the part. Yeah, that's well within 10 microns. And now that we indicated X and Y in for real, we can zero it out, and this is our true position. The final height of the pin after we shorten it is dimensioned off the center line of this bore here, where this piston shaped part runs in. So we take a piece of steel, this is a gauge block, and we just put it between the part, well, our reference cylinder here and the end mill. And now there's a little bit touch and feel. Then I'm just dropping the quill until the gauge block is firmly held in place. And then I lock the quill. Then my cutter is exactly this width of the block above the cylindrical surface here. This is not a high precision touch-off method with the quill, But for what we're doing here, this is perfectly fine. Well, this is a gauge block. I had to use it on its side because otherwise in its normal orientation it doesn't fit in. So this dimension is 8.79 millimeters. The cylinder part here also has a diameter. This is let's say it's 19 millimeters. We're doing caliper here. Let's see, let's get this indicator to absolute. Yeah, it's 19. I have to set the DRO now to half the diameter of the cylinder, means 19 divided by 2, plus the width of the block that I used for touch-off, which is 8.79. That gives me a C value of 18.29 millimeters. From now on, I'm not allowed to move the quill in regards of the C height. Can only use the C-axis. Otherwise my offsets are all messed up. And now we can just whittle away the pin with the 6mm carbide end mill. 2000 RPM, and we're hand feeding and see how it goes. This is, as far as I can tell, it's case hardened. The face of this anvil seems to be very soft, but the outer shell seems to be something like 55 to 60 Rockwell C according to my hardness tester. Oh bugger all, this is not case hardened. This is through hardened all the way. And I think I know why I got a reading for soft on this end of the pin, because I'm the underside where I had it resting on the hardness tester just ever so slightly moved, because the underside here is not exactly super flat. That also explains the nice red glow on the end mill. And I'm not sure if this end mill will make it through this. Okay, now the face of this anvil should be at center height, and I will check that with the mating part after I cleaned off the hardened chips from the bore. And we're very well on center height. As you can see, when I put the mating part with the center hole for the indenter into its bore, the hole in this piston matches or gets split in half by the anvil. This is of course just by eyeballing, but at least we didn't do anything terribly wrong. And the height that I cut this to is not critical. Just shouldn't be off like 6 millimeters. Speaking of 6 millimeters, the final height is not on center height. We need to go 6 millimeters more lower than the center height. So a little bit more of high-speed milling. I whittled down all the material to final height. Now we change to a carbide drill, drill a hole, grind a pin with a step, glue it in, and modifications to the body are done too. I had to get more stick out on the end mill from the collet to clear this bulge in the housing, otherwise would have been a crash situation. So let's change to a carbide drill, figure out our hole position and go for it. And hope we can poke a hole in it and don't have to send it out for RAM EDM. But usually hard drilling into solid stock works okay-ish. This end mill doesn't owe me anything. Blank. 4mm carbide drill, uncoated. Let's see if this goes well, otherwise we have to use a 4mm ball end mill. That's 10mm deep with a 4mm carbide drill running at 2000 RPM and just hand feeding compressed air to get the chips out of the way to not recut them with a drill. This could end quite bad. So, well, that went way better than expected. Obvious problems with setups on the vertical apron, gravity. So when you do a setup like this and you loosen the clamps, think about what you're doing. In this case, I'm starting with the lower clamp, and I'm careful to catch everything that wants to fall down, because we're not amateurs. And now when I loosen the copal clamp up here, part will be free, so better hold it in place. And I'm also holding the shims in place because I don't want to pick up 755 shims. Now since we have machined down the anvil and drilled it, we need to make a pin that stepped down to 4mm. This is a 5mm dowel pin, and Loctite it in there. So stepping down the 5mm dowel pin is of course also good use for the spin fixture, but the problem is when I hold the pin in here and I came in with the fairly small grinding wheels of my surface grinder, the wheel hub hits the screw up here. There are two positions for the clamp of the V-block, one tall and one on the lower side, and this is still too tall in certain diameter combinations to do grinding. Of course, it would be a good idea to make a very low profile clamp that doesn't protrude much above the V-block. That's on the list. It's item number 355, I think. Until then, I have to improvise a little bit. Since I don't have the V-blocks, there are specially extended small diameter V-blocks as an accessory for the spin fixture. I don't have them, but I have a ER11 straight shanked collet chuck with 5mm collet. And I can just use this in here with a packing block. The packing block is just there to spread out the load from the screw on the shank and not bend it. Also, we don't need to tighten these mad tight, just medium tool tight is good enough. And then we tighten the ER11 collet in front here. And woo! Oops, don't. Now we can adjust the V-block along with the collet chuck for runout, and then we grind our 4mm step on here. So let's set it up. Over here on the drill press, rough aligning. So I think I need to go this way. Yeah, okay, that's already way better. Let's get an indicator in. Okay, that's our run out. Now, let's see. Ugh. Okay. This usually works better if you have the clamp in front here, which locks the V-block semi-tightened. And the adjustment works way better. And also you don't get a big jump once you tighten it down. So there we go. Okay. That's a case where a long-handled Allen key would be nicer to adjust the position of the V-block compared to the T-handles, because you get a very short lever arm. So let's mildly tighten the V-block a little bit more, and yeah, that's in a very decent range here. So let's tighten it down finally and call it good. Now we go to the surface grinder, and hopefully I have enough stick out here. Yeah, that's good enough. We need a shoulder length of a little bit less than 10mm. The hole in the anvil of the hardness tester is 3.99, checked with gauge pins. And this pin should be mildly over that dimension. So this is 3.99 and 3 microns over size. The hole I drilled is also it tapers a little bit to the bottom, so it will be a hybrid glue fit, press fit. Perfectly fine here. I shortened the pin to final length and chamfered the ends on the lathe. Now it's time to Loctite it into the body of the hardness tester. I have some acetone here for degreasing. And same for the pin. Loctite is relatively tolerant against oils, but it's still good practice to keep parts clean. Loctite 648, retaining compound. Both the bore and the pin are chamfered, and I put a little bit of Loctite on the chamfer of the bore, so when I drive the pin in, it will pull the Loctite with the pin into the bore. But I'm also wetting the entire pin with Loctite, just to ensure a safe bond. Robin Renzetti recently showed on Instagram that he cut a spiral groove in a part that he Loctited into something else, and he also took it apart with press and showed the excellent coverage of the Loctite on the part due to the spiral groove, allowing to pull the Loctite even deeper into the bore. But in this case, this is just a measuring anvil, so we don't need to go crazy. And I'm just using a copper drift to seat the part into the bore. Wipe off the excess Loctite. And this looks like a relatively clean modification. Time to put this thing back together. I just ground the clearance flat onto this piston part as per the customer sketch. So let's see if we can get this thing back together, and hopefully it still works. The piston has a spring guide on the back, fits in here like this. I have a spring on top, and I think the order of operation is to put the piston in. This is now spring-loaded in the body, and now we can get the handle through there. We don't put the screw in yet. Time for the manual. Let's put a piece of blue tape on here. Then we have the indenter, which is just a pointy bit. This seems to go in here, and poke out the end of the piston in here. Then we have the indenter spring, I guess, goes in, and then this tube nut, this hollow nut. The hardness tester is supplied with a wrench to mount it back together. Now the question is there anything to adjust, or do you tighten it until it's tight? Good question. Next question. I will check that in the manual. So yes, this nut in here is something to adjust. There is an entire procedure written in the manual. Okay, that's the scale. And the last part is the pivot screw. From the other side, of course. I did tape the anvil because I didn't want to the indenter to hit the hardened anvil. But now, since we're all assembled, let's see if we can get a hardness reading with it on some brass. Got it all back together, and it's not calibrated, but it gives a reading. So the idea is you have your spring-loaded plunger in here, and you put a piece of material that you want to test for hardness in here, and then you just squeeze the handle to full compression until it hits the hard stop, and up here you can read the Webster hardness. In this case, it's a Webster hardness of 8. And I'm no expert, but this is a 556 by 45 shell casing, And I suspect that the modification that I did is so the hardness tester can hit on the neck and clear the neck with this large chamfer. That's my suspicion, at least. Didn't ask for a more precise thing, and I can check the hardness on this too. So this is Webster hardness of 7. Well, it's not Webster hardness 7, it reads a hardness of 7. The instrument is not calibrated. It comes with a calibration plate, but I'm not going to do that. I'm not an expert on any of this. I'm going to leave this to the customer. I'm just the machinist that did the modification to this tool. So, well, that was a fun little project, modifying this Webster hardness tester, especially since I have never seen or heard about these. It's an interesting piece of very simple tech, and also we did a modification to the micrometer with the chamfer here. I suspect that's to measure the thickness of the material of a casing right up against the neck, like this. So I hope you enjoyed this little customer project. Thank you all for watching, and I'll be back.